what do you think like the future FPGA will look like?
I think it's a great opportunity to build a career around that. I think that right now there is actually a low supply of FPGA developers.
Really? So with this, you can just take it off into the actual development.
And that's the beauty of the system on module concept.
How do they find their passion?
I think you find your passion through trying many different things. And the good news is in technology, there's no shortage of opportunities.
Hello， 大家好，今天非常开心啊，我们邀请到了 AMD 公司的工业视觉、医疗和科学市场的高级总监 Chetan Khona 先生，我们来一起进行我们今天的访谈。Hi Chetan, welcome to our show. Would you like to say hello to our audiences?
Yeah, thank you very much for clicking and listening to this.
All right, so it's a great pleasure to have you on our show, and today we're going to talk about FPGA in general. So I would like to ask, like in first, as a person, why do you think FPGA is interesting? Why do you, as an individual, like to devote yourself into this area?
Well, so for me, FPGA started when I was in university. And I was in my third year of university, and at that point in time I had worked with microcontrollers, I had worked with DSP processors, and then I got introduced to FPGAs, and my mind was blown because I said, wow, this is really cool and different. You can build anything you want, right? And I think many of us as children maybe played with Legos or something like that, where your imagination can take you wherever you want to go with those toys, and FPGAs are kind of like that for engineers and for developers. And so for me, it was very nice to to do that, and then also to really, as I got later in my time, I learned that you can also do some things more efficiently in FPGAs than you can do with some other technologies.
Interesting. So in your term, what do you think, like in general, what's the main advantages of FPGA?
So I think the main advantages of FPGA, there's quite a few, but I would say if I had to list my top three, I would say flexible I/O. Number two would be determinism, and number three is low latency. And all those things are very important, especially in the business that I represent, which is industrial vision, healthcare, and sciences, because things need to be orchestrated in a timely manner. You know, you can't do things best effort, right? You need to happen on time, and FPGAs enable that better than other technologies.
Would you like to elaborate a bit more on the three key factors?
Yeah, I mean, I think, like, for example, if you take a look at robotics, right? And if you look at, especially nowadays, you have many factories that are manned purely by robotic applications. And so one robot has to work with another one, right? And so maybe if you imagine painting a piece of metal, like maybe a door for an automobile, right? You have to rotate the metal, paint it, rotate it again, paint the other side possibly, right? And that has to be synchronized between the different robots, right? If you have best effort, maybe something won't happen on time and it will paint the wrong color on the wrong side. And so this is a great example, I think, of why determinism and low latency are very important.
So in terms of like, and compared to conventional devices like MCUs you just mentioned, do you think flexibility or like determinism, or what's the unique advantages of FPGA, like compared to MCUs specifically?
So one of the popular applications for MCUs are motor control and drive systems. And I think they work very good for a single axis or maybe dual axis motor control drive system. But what happens these days is more and more you have 4-axis, 6-axis, 8-axis. In a MCU, the performance and the latency and the determinism get diluted as you add more axes of control.
Why is that?
Because you have a single processor or maybe a fixed number of processors, and as you add more control loops, you're then diluting the performance of that processor. So if you compare and contrast that to a FPGA-based approach, an FPGA-based approach is each control loop is individual and done in parallel, and so the impact of one control loop has no impact on the other one, and so you can act completely independently and there's no dilution of performance.
I think that's a great example, since many people is actually asking, like, FPGA is running at much slower frequency, but why it got, a hardware acceleration compared to MCUs? I think you just answered like that.
Absolutely, yeah, the power of parallelism. Right?
Exactly, yes. So you mentioned about a very interesting area like robotics industry and the control and this area. I know AMD is actually launching its new product. So would you like to talk about the new launching and the new product like you just launched?
Yeah, we just recently launched the Kria KD240 drive starter kit and the Kria K24 SOM. Actually, I brought a K24 SOM here, so if you would like to take a look at it. Okay. So you can see it's about half the size of a credit card, and it's quite powerful. It has a quad-core ARM processor, dual real-time processor, memory, both DRAM and flash memory, as well as security functions, all within a very small form factor.
All in this.
All in this, yes. Yeah.
Right.
So it's pretty impressive, and we think that it's great for a number of different industrial applications because, first of all, in addition to its small size, it's also relatively low power. You're talking about 2.5 watts to about 5 watts typical usage, right, in terms of power consumption. So you can do a lot with it, and it's great because it's not the only SOM in our portfolio. We actually have, we call it the big brother to the K24, the K26.
Right.
The K26 is about the size of a full credit card. And you can do much more with it, but sometimes you need to have scalability, right? Sometimes you want to have lower power. This is more geared for things like motor control, DSP intensive applications, where the K26 is a little bit more powerful. It can do AI and some other things like that.
So I didn't see, it's just a black box to me. But in terms of the real applications, how did you deploy it in actual? Because I didn't see any IOs, any wires or board and anything.
Yeah, so the way SOMs work is we have starter kits that we create. And so we have 3 starter kits. We have a motor control drive starter kit, we have a robotic starter kit, and we have a vision AI starter kit. These starter kits are intended to act as a prototyping vehicle, and the starter kits are roughly about the size of the palm of my hand. They have the SOMs on there. Our customers will prototype with them, and then when they go for their own production deployment, they will create their own custom carrier card. And if you can see on there, there's some connectors on the back side of that SOM. They will plug this SOM into their custom carrier card, and that's how they'll deploy and go to production, because it's very difficult for us to predict all the different requirements for all the different customers out there. So somebody maybe wants Ethernet, somebody wants USB, somebody wants both, somebody wants a camera interface, so they can develop a very simple carrier card and then connect it up using our programmable I/O that we talked about before.
Right, it's actually a very interesting idea. I came across the SOM thing previously. I think the beauty of it is you can change, you basically decouple the FPGA and actual applications. We develop something we make FPGA applications on it, but in terms of the actual industrial applications, we have to switch to a completely new board. But with this, you could just take it off from your development board and plug into the actual development.
And that's the beauty of the system on module concept, right? Is that it's really meant for production deployment. And you don't have to go through that translation phase where you throw away all your development activity because you got your application running perfectly on the evaluation board, but now you have to say, okay, start over on this board. And this is a more seamless transition.
Interesting. So, and you also talk about there's another thing. It's the KD240.
240, correct. Yeah. So the KD240 drive starter kit, as you mentioned, is used for motor control drives applications, and so motors are everywhere, right? So if you you think about just coming here today to meet with me, right? How many applications you probably noticed in your day that involves motors? Everything from certainly electric vehicles, certainly power generation, even on the metro, right? The elevators or escalators, or even some of the trains themselves. Motors are everywhere in the heating and air conditioning for this building, right? So there's lots of applications for motors, and so what we wanted to do is have a starter kit that was really just focused on that application so people can prototype their motor control algorithm very easily. And so the kit has all the connections you need. It will plug directly into some like brushless DC motors. You have all the inputs and outputs that you need for that application.
So that's for motor control, and I remember you previously got KV260, right, and KR as well for vision and robotics.
Exactly. So the KV260 is meant for smart cameras. The KR260 is meant for robotics, industrial communication, and control. But really, if you think about it, all three of those kits that you just mentioned are, I would say, complement each other, because also if you think about these days what goes into building a robotic system, you need kind of a robotic brain, you need robotic muscles, and you need robotic eyes. And so if you think about it, those three kits actually serve those three purposes, right? And so it actually, even though individually those applications are very important and critical and very popular in and of themselves, it also together, it speaks to a broader strategy that we have, which is really around, we want AMD to be the most well-known brand in the world with respect to robotics.
So we talk about quite a bit on the hardware itself, right? So we know like the SOM-based solutions, very flexible, it's easy to replace and easy to upgrade. But in terms of the entire ecosystem of FPGAs, like many people are actually complaining, the main pinpoint or drawbacks of FPGAs is very difficult to program. So is there anything like you guys are working on to make it easier to develop?
Yeah, so Kria SOMs are intended to be our outreach platform for those non-traditional users that don't have FPGA experience. What we've heard is that many designers out there have felt that FPGAs offer a lot of value to them, but they don't know how to access that and how to design it because they may not be formally trained in that area. So with Kria, we really tried to holistically look at how we can make it as easy as possible for a non-traditional user. So we support many different design flows, from Python to MATLAB to ROS2 and many more. But also we have an app store where people can download an app and run it. We like to call it the instant gratification of having a successful design with doing very little design effort. And then they can take that design and they can modify it, or they can adapt it to their needs, but at least they have something running that's very successful with very little effort.
So you mentioned about there's some kind of app stores kind of stuff, like people can presumably upload their designs and they can download the IPs or designs from App Store. Would that be both software and hardware as well? It's like,
It is, yeah. There are some apps that are almost all software. There's some apps that are almost all programmable hardware, and there's most apps are probably a mix of both. But all the apps are Dockerized containers. They support and run on Ubuntu Linux. And yeah, you can go to the App Store. You can actually download it directly from the target hardware. So from your starter kit, you don't even need a laptop or PC connected. You just need to connect your evaluation board, your starter kit, to the internet, and it will download the rest.
Okay, but would that be like solely running on the ARM core of this chip, or like they're going to be hardware accelerated as well?
Yeah, so there will be hardware acceleration. So the image signal processing chain, the deep learning processing unit, all those are actually implemented in hardware, but are controlled via software. So you are writing software for the hardware that's been accelerated, and then you can also write software for the application.
Right, that's actually my next question. Right? As a hardware expert or as a hardware engineer, people would like to make full use of the hardware as well. They offload something on the software, but the performance may not be that satisfying, so they offload the rest on using the hardware. But as you mentioned, there's still the possibility to enable the acceleration on hardware. But on what granularity? Can you still program every single LUT or like flip-flops on the FPGA?
You can. Again, we would say that a lot of the folks that are attracted to Kria probably are not interested in that, but we do have very traditional FPGA developers that say, hey, thank you for providing an app store, thank you for providing all these infrastructure, but really I want to do 100% traditional FPGA design with my Kria SOM, and we don't limit you in any respect for that. So you can control every lookup table, every flip-flop, every I/O if you wish. We're committed to Kria SOMs for the long term, right? So we've already stated on our website that we will have a cost-optimized system on module, which is the K24. We'll have kind of a mid-range system on module, which is the K26, and we'll have a high-performance system on module coming in the future. So that will be part of our plans in in future years.
Is there a specific area like for the high-performance module is targeting at?
I think, really, if you look at any of the major design trends out there, right? I mean, high-performance computing, AI, these are all the typical trends out there that people need maximum amount of resources and performance for. So it's logical to assume that that's what we'll target that that system on module for.
Okay, that's interesting. So let's get to the next topic. You just mentioned like you've been looking at industrial health applications and something else as well?
Yeah, industrial vision and health.
But I'm sure like this area is not only using these devices, right? But as a general FPGA market, is there anything for the conventional FPGA, if you like, what's the roles of them to play in this area?
Yeah, so FPGAs in general you see used in a lot of different applications, right? So you see them used in industrial communications. I'll give you one example. So industrial networking, there's many different standards out there. Maybe you or your viewers have heard of things like EtherCAT or Profinet, or some of these industrial communication standards. And there's something like 40 to 50 different standards out there. And it becomes very difficult for a fixed function chip to support all 40 to 50 standards. And it becomes almost a supply chain nightmare because they have to keep inventory of all these different versions. With a programmable device like an FPGA or one of our adaptive SoCs like Zynq UltraScale Plus or Versal, you can essentially program the device at the time of shipment to really support whatever networking standard the customers require. So not only does it solve a technical challenge, but it also solves a business challenge of not having to keep inventory of all these different versions, especially in a fragmented market like the industrial market is.
It's a one shoes fits all solution.
It is, right? And it's very convenient for them.
Is there any trade-offs being made in order to get this flexibility? Is the performance get sacrificed, or is there anything get sacrificed?
So in general, we think that the trade-offs are very well worth it because, for example, performance is typically better in a FPGA-based solution for the reasons we mentioned. You can do some offloading from the processor into the hardware and you get the benefits of parallelism. Also, power can oftentimes be better because you can run also at a lower frequency than a fixed function chip because you're doing things in parallel. Now, what we always say is that if there is a fixed function chip that's available on the market that meets your requirements perfectly, it may be a better fit because it's designed only for that function, right? So, it's difficult for us to say, in every situation, but what we've learned is there's many situations where there's applications that are either underserved because there is no good chip for that application, or like we just discussed with industrial networking, they need the flexibility, and really the value of the flexibility really drives their decision.
Right. I think that brings me to another area which is changing really fast, which is AI. Right. So AI is really changing fast. So many people previously using FPGAs to accelerate AI algorithms, especially inferencing from at the edge computing. Do you think AI is going to make a difference on the area you just mentioned?
Yeah. So I think that absolutely all of our current latest 7 nanometer generation devices have the option to include AI engines, and really also part of AMD, we've made the announcement that we're going to be putting AI engines in some of our x86 processors like Ryzen as well, right? So AI engines are not just a FPGA only technology anymore, but it's really that balance of being able to have a hardened block for some features that aren't going to change, but then add a little bit of programmability around it to adapt to changing requirements. So we kind of make the trade-off to to offer the best of both worlds.
So I think we covered some of the questions or topics, but in your opinion, what do you think like the future FPGA will look like? Will that be bigger, more heterogeneous, like more computing power, or what?
Well, I mean, it just speaks to what we just spoke about with AMD acquiring Xilinx. Right now, Xilinx is part of AMD, is that we're the company that offers x86, ARM, RISC-V, FPGA, and adaptive SoC. So we have all these different technologies, at our disposal. So really, for us, it's about empowering developers with multiple heterogeneous choices so that they can pick the right engines for for what their task is, right? So you can imagine in the future that we will, dig into our bag of ingredients and pull out custom solutions utilizing the best of all these technologies with a purpose in mind.
So because I bring up this question because many of our audiences is actually FPGA enthusiastic and some of them are actually new to FPGA world, but they would like to get involved and learn how to develop FPGAs. But to my observation is that many FPGA books currently is mainly about telling you how to using the EDA tools like Vivado, how to develop your FPGAs and stuff. Would you think as a beginner, would that be still be the very important things to learn how to use the tools? Or like with you just mentioned, like the companies is actually trying to make it more easier to use, or like the beginners should focus on something else rather than just the tool itself. What do you think?
So I think it depends, right, on a number of factors, right? So if you're a university student, right, and you're deciding what you want to focus on, I think it's a great opportunity or a great time to focus on the FPGA tools and kind of build a career around that because, like anything in life, it's supply and demand, right? And I think that right now there is actually a low supply of FPGA developers out on the market, right?
Really?
So I really do, yeah. So I think that if you're a university student and you want to assure yourself, very stable employment, with a nice salary, I think FPGA is a very good area to focus on. Now, if you're already, in industry and you're already, working in Python or ROS 2 or something, then you should definitely take advantage of the, the tools and the design flows that we offer. So really, I think my advice would be is use what's closest to you, right? If the closest thing from where you are today is making use of our new design flows, then go for it. But if you're a university student and anything is possible, I would say there's a really good opportunity in terms of a career and future to go the traditional FPGA route because again, there's not very many of them these days graduating from university. Everybody is doing Java and other things.
So yeah, so my last question, I talk to this like to all my audiences, in terms of like the advice or because at the beginning you mentioned you find your passion on FPGA when you enter the university. So for the audiences, for the new beginners like graduates or like university students, how do they find their passion, do you think?
I think you find your passion through trying many different things, right? I wasn't intending to, I would say, get excited by FPGAs, but my coursework led me there, right? And the good news about it is technology is such a fast-growing field that there is opportunity really for anyone. And I think it's important that you follow your passion because you should always try to do something that is interesting, to you and enjoyable for you because the hours are long, the days are long, right? So we have to, try to do something that is naturally interesting for us. And the good news is in technology, there's no shortage of opportunities.
That's very interesting. Okay, thank you very much for taking today's time to join the interview. Thank you so much.
Thank you very much, Ken. Yeah, thank you.